right, we are back. This is Math 200. We're looking at Chapter 4. And specifically in the note packet, 4.3, page 7. Solving mixture application problems with systems of equations. All right, and so we can do this with, it looks like I kind of set it right up into a full equation and just worked it like that instead of a system of equations. So first, let's do step 1. This is number 2, Hilton University Drama Club. Sold 311 tickets for a play. Students' tickets cost 50 cents each. Non-student tickets cost $1.50. If the total receipts were $385.50, find how many tickets. So this is a mixture problem. We're going to say step 1 is set up your variables. So student tickets, again, if you want to be clever and call it S or T or something, I just usually go with X. And then non-student tickets, I'll call it Y. And so I'm actually adding to the notes because I skipped a step. Now, when you have mixture problems, this is always your first equation. Like that plus that equals the total amount, in this case 311. What I did was when I set up the problem, I circumvented this step. I instead of calling it X and Y, I referred to it as, I solved this one for Y, subtract X from both sides, and Y is equal to 311 minus X. And so I just put in both of them in terms of X right off the bat, and then basically used the substitution method. So if you look at the note packet, I have this listed as 311 minus X, and there is no Y. I skipped that step, all right? So what I'm doing, though, is the substitution method. X plus Y equals 311, and then we do the money one. That's 50 cents times X, however many tickets they sold at 50 cents each, that contributed. And then $1.50 times Y, and then that, normally a true mixture problem now would also have a calculation on this side. So this is a variation of a mixture problem where they gave us the total receipts, $385.50. So the 311 didn't work into that at all. This was just given to us. Okay, so now we're going to basically, this was one equation, this is the other equation, and we're using the substitution method where I'm going to take this and substitute it in where you see Y and then figure it out. Remember what that does, that tricks it out to be all X's. And so now I'm going to solve that. That's step 2. Is get it set up into an equation. There's my equation, and now I'm going to solve that equation. I'm going to do the distributive property. So I got 0.5x, and I already clicked that into my calculator. That's 466.5. So 1.5x is equal to 385.50. I'm just going to call it 0.5 for now. Combine like terms, put those two together. So that positive 0.5 and negative 1.5 on the same side is negative 1x. 466.5 equals 385. 0.5. Subtract 466.5 from both sides. Negative 1x is equal to negative 81. And then divide by negative 1. So X is equal to 81. Now what does that mean? Well, that means there were 81 student tickets sold, because X was student tickets, so 81 students tickets, which means that the majority of the 311 came from non-students. 311 minus the 81, right? That says 311 minus 81 is the Y. And so that is going to be the non-student, 230 non-student tickets. Okay. And so now you should check your answer. And that's step 4, is check your answer. So step 2 is set it up. Step 3 was solve it. So this was step 3. And now step 4 is check. which means I know this and this add up to 311. That's not really the check I'm after. We should check it on the money one. So we pop in 0.5 times 81 and then add 1.5 times 230. And that should work out, let's see, that's 40.5 plus 345, which is 385.50. So it checks out. And so that's step 4, is the check. And it does work out to be the 385.50. All right. Lovely. Let's look at a couple more mixture problems. So Terry Watkins can row about 10.6 kilometers in 1 hour downstream and 6.8 kilometers upstream. Oh, not per, oh yeah, in 1 hour, okay. In 1 hour, all right? So 1 hour, both of them 1 hour. And let's see, what do they want us to find? Find how fast you can row in still water and find the speed of the current. So there's two things going on here. Let's look at step 1 here. This is distance formula equals rate times time, but we're going to actually do two distances. Distance equals rate times time. So when you're going downstream, that means the water's pushing you. So you're supplying the power, but then the water's pushing you, and that's the extra part. All right, so I'm going to say in the context of this problem, X is equal to the current. Okay, so 10.6 is the downstream one, and that's going to be R, however fast he's rowing, plus the current is pushing him, and T was 1 hour. So that's basically one of our equations. Against the current, he only goes 6.8 kilometers, R minus X, so it's fighting him. It's taking however fast he's rowing, and it's subtracting that same amount. And that's still times 1, they said, in 1 hour for time. All right? So now, check it out. This should look familiar really soon here. So I have this. I'm going to rewrite it, so it's R plus X equals 10.6, and this, R minus X equals 6.8, and this is step 2. Set up your equations. Well, this kind of set them up by labeling them into distance, rate, and time, and identifying X as the current. This was sort of the setup. All we had to do was do 1. Now, if they would have said, hey, it took them 2 hours to do that, it would have been fine. Then we would have 2R plus 2X equals. That's all. So it doesn't matter if the times were different or not. So there are 2 equations. Now this one is screaming out, right? The elimination method, you add straight down and the X's disappear. We don't even have to multiply it by anything to get them to go away. So we add straight down, 1R plus 1R is 2R, 1X plus negative 1X is 0X, so they're gone. And then we got, 17.4? And then divide that by 2. So we found R. R was his rate. That's how fast he was rowing. So he's rowing at 8.7 kilometers per hour. All right. How fast was the current going? Well, we don't know that, but we can find it out pretty quick. Just put it into either one of those equations. We'll do the R plus X equals 10.6. And so now we're going to take our answer from here. We're going to sub it back in right there, just like when we found the points that were crossing. So X equal to 10.6. Where the 2 lines were crossing at a single point, it's the same thing. I mean, in different variables. Well, X is the same. All right, and so X is equal to the current. Now, I know the current had to be going slower, 1.9x. Now, how did I know that? You have to, or no, X is equal to 1.9, not 1.9x. 1.9 kilometers per hour. Okay, how did I know it was 1.9 would be it had to be less than 8.7 because otherwise he wouldn't have went anywhere. It would have pushed him back the other way. So we knew the rate had to be stronger than the current. Otherwise, he wouldn't get 6.8 kilometers. He would be going negative. It would have said it pushed him. He couldn't beat the current. All right? So then that was step 3, was solving. We did step 3 and solved. And then step 4 is check. And so to check that, we just put in 10.6 is equal to 8.7 plus 1.9 times 1. It is, that's 10.6 equals 10.6. And we could check it against the other one also. 6.8 is equal to 8.7 minus 1.9 times 1, which is 6.8. So it checks out. All right. Okay, another mixture problem, literally with us mixing stuff. Candy, M&Ms, and trail mix. And so I think this one is a true mixture problem. It's not a pseudo mixture problem. Like the one with the ticket prices, it was almost a mixture problem, except they gave us the total amount. We didn't have to calculate that on the right side. This one is mixture all the way. So let's take a look at example 4. We've got step 1 here will be fancy. I'll say M is equal to M&Ms instead of using X. And T is equal to trail mix instead of using Y. If you want to use X and Y, I don't care. Just make sure you label them up on the top one so you remember which is which. This one now, it'll be obvious which one's M&Ms and which one's trail mix. All right, so step 2, get them set up. So we're adding M&Ms and trail mix, and we want a grand total of 50 pounds of candy. And now they want to know how much M&Ms do I put in and how much trail mix do I put in to dial it into this certain amount. They want to have it worth $1.80 per pound, and then they probably sell it for more, right? You upcharge that. So maybe you sell it for $2.25. So they make some money on each pound of candy. They don't want to just break even. So now look, M&Ms cost $2 a pound. So we put 2 times M. We just take this structure, this M plus T equals 50. We take that exact same structure, and now we insert the money into it. So 2 times however many pounds of M&Ms plus $1.50 times the trail mix is equal to, they want it to be worth $1.80 total. So $1.80 times the 50. This is a true mixture problem because see, 50 got into the act. Where with that ticket problem, they just gave us this number and it wasn't really related to the one that we had, the 311. All right, this is a true mixture problem. So now we have this. M plus T is equal to 50. 2M plus 1.5 T is equal to, and you take $1.80 times 50, and that's 90. So these are my 2 equations, my 2 linear equations. Step 2 is now done, so now step 3 begins where I want to solve for this. Now, me personally, you could do, a lot of people are like, oh yeah, look, subtract M, 50 minus M, put that in right there, use the substitution method, we're golden. You could totally do it that way, that's fine. I usually don't do it that way. I usually do elimination. I'd say, let's get rid of the M. So how do I get rid of the M? Well, I leave this one alone, 2M plus 1.5T equals 90. But now I'm going to go on a vision quest. I don't want M, I want the opposite of this. So I want negative 2M to happen up there. So what do I have to do to this to get a negative 2M? Well, I have to multiply everything by negative 2. Not just that, everything. This side of the equation and that side of the equation. So negative 2M, negative 2T, and negative 100. Now I add straight down. The M's disappear. I get negative 0.5T is equal to negative 10. I divide by whatever's in front of my variable, negative 0.5. And T is equal to 20 pounds. So what does that mean? T is equal to 20 pounds. Well, we know T was trail mix, right? So that means 20 pounds of trail mix. And then how much of the M&Ms? Well, we have 50 pounds total, right? So you could put it back into that equation if you'd like. Don't put it into this one. Let's put it into that one. So we've got M plus 20 equals 50. Or some of you just did that in your head, right? You just said, oh, it's got to be 30. It's 50 total, so it's got to be 30. It's fine. Either way, you can think of it as subbing it back in and solving. So M&Ms, 30 pounds of M&Ms. All right. So that was step 3. We solved it. And step 4 is check it. And so the check on this would be with the money then. We'd say 2 times 30 for the M&Ms plus $1.50 times 20 for the trail mix. That should equal $90 that we got the 1.8 times 50. And I believe it does. 60 plus 30 is 90. Yep. So it checks out. We're good. All right. And that also makes sense that, look, we needed more of the M&Ms than we needed of the trail mix because $1.80 is closer to $2, right? $1.80 is only 20 cents away from $2, but it's 30 cents away from $1.50. So if $1.80 is what we want at the end, there's going to be more of this than that because this number is closer to that number. All right. If it would have been exactly in between, if it would have been $1.75, then it would have been exactly the same amount. Then it would have been 25 pounds each. Okay. But it was not. It was a little closer to the 2. Awesome. Let's see. Oh, that's 17 minutes. Okay. So we'll do the next video. Will be